All right, it's our lab lecture for chapter 9. So part of the reason that we've been talking about all of this is to talk about periodic properties on the periodic table, why it's called a periodic table. The chemical properties of the elements are periodic because the number of valence electrons is periodic. So elements in the same column have similar properties. Elements in the same column have similar properties. Also, the same number of valence electrons, at least for our main group elements. For our transition metals, we looked at on the previous slide in the last lecture, sometimes the numbers are not what we would expect, and so that can affect the number of valence electrons that we have. So the elements that are in a period or in a row show a pattern that repeats. So if we look at elements in a column, they should all display similar properties because they have similar or the same number of valence electrons. And that's why we have group names and why groups behave similarly. So our noble gases, for example, have 8 valence electrons, full shells. All of the orbitals for our noble gases are going to be full. They all have either 1s2 or 2s2, 2p6. And so these are especially non-reactive. Helium and neon especially are practically inert. They basically will not go through chemical reactions unless you really, really try. This is part of why we use helium in party balloons. You can fill a balloon up with helium. If the balloon pops, it's just full of helium. Helium is inert, it's non-reactive, so it's not going to do anything. Hydrogen gas is also lighter than air, and so you can fill balloons up with hydrogen gas and they'll float. Hydrogen is not non-reactive, hydrogen's flammable. And so if you pop a party balloon, especially if it's like right next to a birthday cake that's got candles lit, you're probably going to end up with an explosion. And that's going to be really surprising to everyone, even if it wasn't a surprise party. And so that's part of why we use helium for party balloons. For more on the explosiveness of hydrogen, look up the Hindenburg. Atoms with 8 valence electrons, or 2 in the case of helium, are particularly stable. Full valence shell is stable. So what a lot of the other elements want to do when they go through reactions, things like metals, nonmetals, metals losing electrons, nonmetals gaining electrons, what they're striving for is to become like a noble gas. Noble gases are the millionaires or billionaires of the elemental world. Everyone wants to be like them, or at least lots of people want to be like them. So noble gases are non-reactive because their electron configurations are really stable. Alkali metals, our first column, our 1A metals, are very reactive. The electron configurations are close to those of noble gases. They just have one extra electron. So these are all noble gas plus 1 electron. And so if you get rid of that 1 electron, now you've got a noble gas electron configuration that's especially stable. And so alkali metals are going to lose that, whatever level it is, S1 electron. So that's why they form things that have a 1+ charge, all of our alkali metals, because they're losing 1 electron, they're getting that noble gas configuration. And so this is why these metals are especially reactive. Some of these, like sodium and potassium, if you put them in water, they like light on fire with how reactive they are. Cesium explodes. On the other side of the periodic table are halogens, right next to the noble gases as well. These are 1 electron away from noble gas. They just need to gain 1 electron. And gaining 1 electron, like losing 1 electron, is also not especially hard. So halogens have 1 fewer electron than the nearest noble gas, the next noble gas. So these tend to gain 1 electron. When they gain 1 electron, they get the noble gas configuration. So these form 1 negative charge. So these are all also very reactive. So there's a bunch of metals and nonmetals that form 1 ion. And the charge that these ions form is predictable. It's based on the position in the periodic table. Our group 1A forms a 1 plus, our group 2A forms a 2 plus, our 7A forms a 1 minus. They need to gain 1 electron to become a noble gas configuration. Our group 6A, our oxygen group, needs to gain 2 to become a noble gas. Gaining 2 electrons, electrons are negatively charged, and so they take on a 2 minus charge. So this is where we get the ions that form only 1 charge from. So group 1A, 2A, 7, 6, 5. This is the idea behind our main group elements that form 1 charge for their ions. They don't form multiple charges. It's because of their electron configuration and how many they would need to gain or lose to become a noble gas configuration. Our anions are formed when they gain electrons. So sulfur has 6 valence electrons. It wants to get up to 8 valence electrons because that's the noble gas electron configuration. And so it has to gain 2 electrons, so it'll form an S2 minus ion. This is the previous couple of slides, but just with a specific example for an anion, a negatively charged ion. We also have a similar thing for our cations, just the opposite direction. Cations form when the metal atom loses its valence electrons. This results in a new lower energy level valence shell. So magnesium, for example, has 2 valence electrons. When it forms a cation, it loses its valence electrons. It's got 2 valence electrons. It loses those 2. And so it forms a 2 plus charge. We're stripping off the outer electrons versus adding electrons like we do in our anions. This is important for some atomic trends that we'll talk about. So one of our atomic trends is atomic size. And there's a couple of ways to define atomic size. One of the ways to talk about it is non-bonding atomic radius, or van der Waals radius. Van der Waals radius is if you've got atoms that are sitting next to each other. They're not bonding to each other. They're just sitting right next to each other, like in krypton. It's half the distance between nuclei. There's also the bonding atomic radius or the covalent radius. So for nonmetals that form things like Br2, it's half the distance between two of the atoms bonded together. So the distance from the nucleus to the other nucleus, cut it in half. It's essentially how far do you have to get before the two electron clouds are meeting. For metals, it's half the distance between two of the atoms next to each other in a crystal of the metal. In all of these, basically half the distance between nuclei. The distance from the nucleus to the edge of that atom. They're slightly different from each other. The non-bonding atomic radius is going to be bigger because they're not, the atom is not overlapping with its neighbor. So this radius is going to be bigger than the bonding atomic radius or the covalent radius, because in these they're overlapping. So if you could take a van der Waals radius and a covalent radius, van der Waals should always be a little bit bigger. The atomic radius is an average of the radius of an atom based on measuring a bunch of elements and compounds. This is always going to be smaller than the van der Waals radius because the van der Waals radius is the biggest size, the most separated that the atoms or the nuclei can be from each other. And since we're averaging, the atomic radius will always be a little bit smaller, not especially important. Could also be an approximate bond length being the sum of the atomic radii of different bonded atoms. So take a bunch of different compounds, measure how far the nuclei are away from each other, average them together, and you can get an approximate bond length. The how of how we get those numbers is not especially important. What's more important is the trend. So the trend is the important part. And for our main group elements, atomic radius increases down a group. So size increases down the periodic table. So if we're looking at an up-down trend, the further down you go, the bigger the element gets. So if we look at our alkali metals here at the top, lithium all the way on the far left. Below it is sodium, sodium's bigger. Below it's potassium, potassium's bigger. Below it's rubidium, rubidium's bigger. Below it's cesium, cesium's bigger. So anytime you're moving down, we're adding, if we think of our Bohr model, we're adding shells. So it makes sense if you're adding shells on, it's going to get bigger. You're adding another coat of paint to your little ball of paint. So it's getting bigger. For main group elements, the atomic radius decreases across a period. So when you're moving from the left side of the periodic table to the right side of the periodic table, adding electrons, adding protons, the size gets smaller, which is not what we would probably expect. We would expect, okay, you're adding stuff on, it should get bigger. That's not what happens. Why? All right, so this has to do with what we were talking about earlier, which is Coulomb's law, and it has to do with shielding. So shielding is a part of it. So in a multi-electron system, if we've got more than one electron, electrons are attracted to the nucleus and repelled by each other. So we've got our nucleus in the middle. Our nucleus is all of our positive charge. And then I'm going to draw an inner shell. I don't know why it looks like a sideways egg. This is our core electrons. And these basically cancel out protons in the nucleus. This is the shielding effect. And then on the outside, we've got some electrons. I'm drawing our Bohr model. It's the quantum mechanical model that we're actually using, but the Bohr model is really convenient for explaining it. So we've got these electrons on the outside. All of the electrons on the inside are repelling these electrons, pushing them away. They're also being attracted to the nucleus, so that's pulling them in. So overall, they're experiencing a net pull-in, because there's always going to be more protons in the nucleus than there are core electrons. So out here on the outside experiences a partial positive charge. This is the effective nuclear charge that we were talking about earlier. So if we look at lithium, we've got our nucleus. It's a 3 positive. We've got 3 protons. We've got 2 core electrons. Those each cancel out one of these positive charges. And so for our 1 valence electron, this is experiencing the 3 positive charge minus the 2 core electrons. And so it's experiencing a 1 plus charge on this valence electron. So it's pulled in with a force of 1, whatever the numbers would be. We could calculate it. We're not going to calculate it right now. What happens to the effective nuclear charge as we move from the left side of the periodic table to the right side? If we look at adjacent elements like phosphorus and sulfur, how many core electrons does phosphorus have? 10. Phosphorus has 10 core electrons because that's the previous noble gas, which has 10. How many core electrons does sulfur have? Also 10. Phosphorus also has 10 core electrons because neon is still the previous noble gas. What does sulfur have compared to phosphorus? What changes from phosphorus to sulfur? The valence electrons changes. What else changes? The size changes, but that's because of we're also gaining a proton. So we're gaining a proton, the core electrons are staying the same, and so the effective nuclear charge is going up. Which I'm jumping the gun a little bit. So effective nuclear charge is the net charge that is experienced by an electron. And it has this formula, if you wanted to memorize the formula. I don't think I give you this one. So effective nuclear charge is the number of protons minus the core electrons. I've drawn this up a couple of times, just not with these exact terms. Valence electrons also make a small contribution to shielding. We're going to just ignore it for the sake of simplicity. So what are the effective nuclear charges of nitrogen and argon? For nitrogen, we have 7 protons. Minus how many core electrons? 2. So the effective nuclear charge is 5 plus. And what about for argon? Effective nuclear charge is what? 18 minus the previous noble gas has 10. So 18 minus 10. So the outermost electrons, the valence electrons, are going to experience a force, an inward pull force of about 8, as opposed to the 5 that we'd experience if we're in the nitrogen group. So our explanation for the trend in atomic radius, when we're moving down a column, we're adding shells. The principal quantum number increases, we're getting bigger orbitals and larger atomic radius. So we're adding shells, that makes it get bigger. When we're moving across a period, the effective nuclear charge increases. This results in a stronger pull on valence electrons. So the outermost shell of electrons, as you're moving across the periodic table, the pull is increasing, and so it's shrinking in size as you move across the periodic table. So it's shrinking left to right. It's getting smaller left to right on the periodic table. So size increases down and to the left. If you just want to memorize something. Questions about radius or effective nuclear charge? All right, we also have trends for the transition metals. For these, the size increases down the column, just like the main group elements. The radius of the transition metals is roughly the same size across the D block. So across the D block, we're adding core electrons. At the same time as adding protons. So effectively, every time we're adding a proton, we're also adding a core electron, and so the effective nuclear charge is about the same across. So the size doesn't change much for left to right. All right, for atomic size, let's make some predictions or choose the larger atom in each pair if we can. First one up, we've got tin. and iodine. Which one's going to be larger? Tin. It's further to the left. It's got less effective nuclear charge. It's got lower effective nuclear charge, so it's going to be bigger. Size increases right to left. And what about germanium versus polonium? Which one's bigger? Because they're not just up and down or left and right. Which one's bigger up, down? PO is bigger up and down. And which one's bigger left, right? GE is bigger left, right. What do we think makes a bigger difference? Adding on a whole other shell or slightly changing the effective nuclear charge? Adding a shell is probably a bigger effect. So polonium, probably the bigger of the two, because the up-down is probably a bigger effect than the left-right, at least with how different these are. And then what about chromium or tungsten? Tungsten, because it's further down. We've added on 2 more layers of electrons. Questions about any of those? Okay, so that's atomic size. We also have electron configurations for ions. So this is probably something you didn't do in Chem 20, so this is new for Chem 1. So remember that anions form when atoms gain electrons. Anions are negative charge, and that results from gaining electrons. So since we're gaining electrons, we're going to add electrons. For each negative charge. Cations form when the atom loses electrons, because cations have positive charge. So we're going to subtract 1 electron for each positive charge when we're doing the electron configurations. So one way that we can go about doing this, you could count up the number of electrons, take into consideration the charge, just figure out the number of electrons for the ion, and then do the periodic table energy filling order to get it. Or what might be easier for us is to do the electron configuration for the neutral atom and then subtract the number or add the number of electrons for the charge. So the aluminum atom has all of this. It's past the first row, 1s2. It's past the second row, 2s2, 2p6. It's in the third row, 3s2, 2, and then we jump over to 3p1. It's the first spot in the 3p, row 3 of the p block. For the 3 plus ion, 3 plus means subtract 3 electrons, and we're going to take those off of the end. We're stripping off all the valence electrons, and we're left with basically just the electron configuration for neon. And then its orbital diagram would be this. It's just a full 2s and a full 2p. So that is for our main group. We can also do it for transition metals. For transition metal cations, we remove the valence electrons first. So we're moving from the highest n number. When we're moving across our d block, remember that we're filling up core orbitals. So instead of removing from our core orbitals first, we're going to take off from our s block that we would have counted up from the far left of the periodic table. So for an iron atom, our highest n number is n equals 4, or 4s, 2. So the valence electrons are lost first, so these 2 electrons come off first. So if it's an iron 2 plus cation, we've now got 4s0 because we took off those 2 electrons. So we just removed the 4s entirely, and now it's 3p6, 3d6 that's written. If we take off another one, then it comes off of our D shell. And if we removed more, it would also come off of the D, the 3D. So for our iron 3 plus, or ferrous ion, we'd have an empty 4s, and our 3D would have 5 in it, so that's all upspin. Parallel first, and then we would double them up after. And this can tell us something about the magnetic properties of transition metal atoms and transition metal ions. So you may know that some metals are magnetic. If you take a magnet and you stick it onto some metals, especially iron, iron tends to be magnetic. You stick it onto those, it'll stick. Some other metals, though, are not magnetic. So if you try to stick them on to a different metal, it might not be magnetic at all, which is sometimes frustrating, like just annoying. This has to do with the electron configuration. So an atom or an ion is paramagnetic if it has unpaired electrons. So para maybe meaning parallel, and parallel would be unpaired. So paramagnetic atoms or ions have unpaired electrons. And these will be attracted to a magnetic field. There are also diamagnetic fields. Di like 2. Or opposite, I think, is also another way that di is used as a prefix. These are going to have electron configurations where all the electrons are paired. So the 2 meaning both up and down, or opposite meaning 1 up, 1 down. I would recommend memorizing these terms. So diamagnetic means that it's all paired. And these will be slightly repelled by a magnetic field. It's not a strong force. It's probably not something that you would notice. So that it's easier to find later, we'll write memorize in a big box. Question?
Yeah, why copper isn't magnetic? Because the D field is electrons.
Possibly, yes. It's been a while since I've done a lot of transition metal chemistry. But yeah, I would expect so. One of my favorite demos, actually, which I have at home with my dangerously strong magnets, which I don't think I've mentioned yet. If you take a piece of copper pipe and a piece of PVC pipe, if you take a really strong magnet and you drop it through the PVC pipe, it just falls straight through. If you drop it through the copper pipe, as it's moving, it generates an electric current. This is not actually related to this. It's more moving particles create magnetic fields. When it moves through the metal pipe, because copper is not magnetic, it doesn't stick, so it'll still fall, but as it's moving, it generates a magnetic current that's opposite, and so it actually repels it as it's falling, and so it takes a lot longer to fall. But it's a physics demo, not a chemistry demo, so I have no reason to bring it to school and show it off. But I finally bought this stuff, and it's really fun. And I showed it I've showed it to other people that are also like science educators, and they're like, oh, that's so cool, I love that. But they are dangerously strong. I've hurt myself with the magnets because they jump like long distances to each other, and really strong magnets tend to pinch you really strongly. Anyway, whole extra sidebar. But yes, diamagnetic, probably why it's not magnetic. All right, electron configurations. Let's do electron configurations and orbital diagrams for each of these ions and predict whether they'll be paramagnetic or diamagnetic. So the first one up, we've got cobalt, 2+. Cobalt, its previous noble gas, is argon. We're going to do it for just cobalt, and then we'll modify it to be 2+. So after argon, we're in what row? We're in row 4. The first thing that we encounter, what block do we encounter first? S. So 4s. We're past it. There's 2 spots. So 4s2, and then we're in the D block. What number are we putting with our first D block? Is it 4? Is it something else? It's 3. It's our first row. D shows up for the first time in n equals 3. Or it's row -1. So we're doing 3D. And then what spot are we in? We'll count over. 1, 2, 3, 4, 5, 6, 7th spot. So it's 3D7. So this is just for cobalt. How are we going to modify it for 2+? Are we adding or subtracting electrons? We're subtracting electrons. How many electrons? Subtracting 2 electrons. So what does our electron configuration become? Where are we subtracting those 2 electrons? Valence electrons. That's true. We are subtracting our 4s2. So we've got 2 electrons that we're removing. We've got 2 electrons in our 4s. So get rid of those. And the electron configuration AR3D7. So our orbital diagram, argon, empty 4s. Then we've got 3D. How many boxes do we draw for 3D? 5. D gets 5 boxes. We have to add in 7 electrons. We're going to fill them in with parallel spin first. So our first 5 are up. And then we add in 2 more, and those get paired. Are they entirely paired? Are they all paired electrons, or do we have some unpaired electrons? We have some unpaired electrons. Is that paramagnetic or diamagnetic? It is paramagnetic. So we would expect it to be attracted to a magnetic field. Then we've got the nitrogen ion. Nitrogen shows up in row 2. We'll go ahead and use the shortcut for helium, even though it's a little bit silly. Then we're in row 2. We encounter our S block. We're 2 spots in the S block. We're past that. And then we're in the 2p. So 2p, 1, 2, 3, third spot. It'll be 2s2, 2p3. And we've got a charge. We have to account for the charge. What does the 3 minus tell us? Add how many? 3 electrons. So we're going to add 3 electrons. So this would become helium, (2s2), 2p6. And then doing our electron configuration, we've got 2s, we've got 2p, and they're all full. Do we have any unpaired electrons? So they are all paired. So what do we call this? Diamagnetic. So it would be slightly repelled by a magnetic field. Question?
Will there ever be a case where you add electrons to an anion and you have to add a shell? Or will it always stay within?
It could happen. we're generally not going to see that happen. Generally, it's just going to add until it maxes out the shell. You can make it add less than up to that. So like we could have N2 minus, which would be weird. We could also have N4 minus, which would also be weird. Generally, that doesn't occur. It's generally going to be N3 minus. Okay, so beyond just atomic size, which we would have talked about in Chem 20, you should have talked about in Chem 20, there's also trends for ionic radius. So for ionic radius, cations are much smaller than neutral ions. The reason for that is when we're making cations, like with sodium, if we're subtracting an electron, we're basically pulling it back a row to neon. We're taking off the outer shell for cations, generally. We're removing a shell, we're removing a layer, and that's going to make it smaller. This also results in it having higher effective nuclear charge for anything that's left. Even if we're taking a beryllium and not making it a 2+, if we're making it like beryllium plus, because we're removing an electron, it's still going to get smaller because we're increasing the effective nuclear charge, the valence electron shielding effect and all that. So here we've got radii of atoms and their cations. So atoms is on the left, lithium plus is much smaller. So it goes from 152 to 60. Beryllium's even stronger. It goes from 112 to 31. So you can see the atoms on the left are all much bigger than the cations that are on the right. So cations get smaller. For anions, the anions are much larger than the neutral atoms. Adding electrons lowers the effective nuclear charge. Even though we're not adding to the core electrons, we're adding valence electrons. The valence electrons still shield each other a little bit. And so that causes it to expand. We're reducing the amount of positive charge that they experience. So positive ions are smaller. Negative ions are bigger. We've got the same comparison groups over here. We've got the atoms on the left, their anions on the right. We can see the atom is always smaller than the anion. It's a pretty drastic change in size for some of these as well. There's also the more confusing isoelectronic. Actually, these are not more confusing. It's just weird because we're comparing different charges and uncharged things. Isoelectronic ions, iso meaning same, and electronic being the number of electrons. So an isoelectronic series is elements that have the same number of electrons. So we're looking at positive charge, neutral, and negative charge typically for these. And because they have the same number of electrons, the one with more protons is going to have the highest effective nuclear charge, and so it's going to have the smallest radius. This sort of fits with our trend for ions just from the previous slide. Positive ions are smaller, negative ions are bigger. This also works for our isoelectronic series. So for S2 minus, it's going to have the electron configuration of argon, going to have 18 electrons. Chlorine We're adding 1. It's also going to be like argon. Argon obviously would be like argon. And we could also have potassium with a 1 plus charge. We took off the 4s1 electron, so it's like argon. Calcium we took off 2, so we took off the 4s2. So it's also like argon, 18 electrons. Sulfur is getting bigger because it's gaining electrons. It's a negatively charged ion. Negatively charged ions are bigger. Chlorine gained fewer electrons, so it's not quite as big. And then potassium, potassium lost 1 electron, so it's smaller. Calcium lost 2 electrons, so it's smaller, but twice. Would be another way you could think of it. Questions about those? Very fun to have more trend stuff to memorize. Okay, I'll give us some time to work on choosing the larger atom from each of these pairs. Okay, choosing the larger atom or ion from each pair. We've got K and K+. Which one do we think will be bigger? Potassium, just potassium. Potassium is larger. The potassium ion loses its outer shell. We're pulling off that 1 valence electron, and now it's just we're pulling off this outer valence electron. Now it's like argon. It's gone down 1 n number. It's still got the same number of protons. It's going to be drastically smaller. Its effective nuclear charge goes way up. What about for fluorine or fluoride? Which one's going to be bigger? I'm bad at reading lips, so saying fluorine or fluoride quietly, I can't tell. I think we said fluoride. I'm hoping that we said fluoride. Fluoride is larger. F minus gains an electron. So we could think of that like we're adding on. What's actually happening, we're lowering the effective nuclear charge because there's a little bit of shielding added. That causes it to blow up in size. And then which is going to be larger, calcium ion or chloride? This is an isoelectronic series, or an isoelectronic set of ions. Chloride is going to be bigger. Cl minus is larger. Positive ions are smaller, get smaller. Negative ions get bigger. So that trend works for comparing a neutral versus an ion, as well as comparing isoelectronic ions. The positive one's going to be smaller, the negative one's going to be bigger. Any questions at all about gestures generically? Okay, then we'll stop there for today. We should be able to finish this up in lecture on Wednesday.